So if you look at your sheet, there's some definitions. The first one is set. So when you talk about a set, it's just, the definition says it's a collection of objects or things. I could refer to this class. This is Collins's 9 a.m. class. And you would be the elements in the set. Each one of you will be elements because elements are members of whatever set I'm defining. And if I define the set to be my 9 a.m. class, you guys will all be members in that, and we refer to that as elements. Now, there's certain ways we write these. A set is defined with a capital letter, so I could say A, and I could say A is equal to, I put this brace up here. This brace represents, it tells me that I'm going to start putting the elements of the set in there. Braces like that represent sets. So now I could just start putting names in here. I could put, Jody, John, comma, and I could keep listing names of Collins's 9 a.m. class, right? This way of listing the names is called the roster method or roster notation. So a roster method or a roster notation, it just lists the elements that are in the set. Then you put commas between each element, and that's a roster notation to represent a set. We only work with well-defined sets. So what's a well-defined set? If I say the set of you guys, my students in the 9 a.m. class, that's a well-defined set because regardless if anybody went and asked and listed all the names of the students in this class, everybody would get the same answer. We'd all get the same thing. If I say, tell me the set of U.S. presidents, and I told you to list them, well, after you went to Google and looked them all up, we'd all get the same one, right? I mean, it wouldn't be, we wouldn't all be able to name them now, but it's well-defined because we'd all come with the same presidents if we had to list all the presidents. If I said, list the worst presidents, well, that's not well-defined because my worst president would be different than maybe your worst president. So that would not be a well-defined set because it's a matter of interpretation. Anytime we have something that you could interpret differently, if I could say, oh, tell me the prettiest people. Well, that's an interpretation. So anything that you could have an opinion about or is a matter of interpretation is not a well-defined set. All the sets we're working with are well-defined. It would be hard to work with anything different. So they'll all be well-defined. So here's our roster notation. Let's look at set builder notation. Set builder notation is a way of representing the set mathematically, kind of describing the set. So I could say, let's say B is equal to, and this is going to say X such that X is Collins's 9 a.m. class. So in set builder notation, you read it and you say X, and then this line right here means such that. So now we're going to define X or describe what X is. So we define X and we say such that X represents Collins's 9 a.m. class. So now I've described it. Now you can list all the elements in the set, which is all you guys, and we would have the same thing as if I would list it in roster notation. They mean the same thing. Another way we use set builder that you've probably seen before is something like this. I could say set C is equal to X such that X is greater than 2 and X is an element of the natural number. So you're like, okay, there's a lot in there. So what's all that mean? First of all, this notation right here, so this right here means element of. So that little e, it's a way of saying element, and we'll show that more in a minute. So what this is saying is it's saying I want all the x values that are greater than 2 that are also in the natural number system. And you're like, okay, well, let's refresh ourselves what the natural number system is. So the natural number system, it's the ones that come naturally. So what comes naturally when you start counting? Yeah, they start with 1, 2, 3, 4. They're also called the counting numbers. So it's the set of natural numbers would start with 1, then 2, then 3, and then dot, 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 which means it continues on forever with that same pattern. The dot, 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 that means it continues on that way. So natural numbers start with 1. X is greater than 2 and is a natural number. So that means it's in this system, in this number system, but it's only values greater than 2. So if I were to list C in roster notation, I would start with what number? 3, because this is greater than, strictly greater than. That means it does not include 2. So the next larger number is going to be 3, and then 4, and then 5, dot, 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 and it's going to continue on that way. Page 49 in your book. It has a review of all these set builder notations and then how to put them in roster notation that, with all the inequalities. So if you're not very good at inequalities, you want to look at 49, go to the multimedia library, and then go into chapter 2 and then look at page 49. But let's do another one. I just kind of want to tell you where to look. Let's say set D. Let's say set D, I'm going to say X such that X is greater than or equal to 3 and X is less than 5. So I put that set up there. I ask you to put in roster notation. So I'm going to say set D in roster notation is going to start with what number? 3, because 3 is included. So I go 3, then 4. Can I put 5? No, because I also want X values that are less than 5. See, strictly less than 5. So I don't include 5. I just end it right there. So set D only represents the numbers 3 and 4. E is equal to the set X such that X is less than 0 and X is an element of the natural numbers. So X is in the natural numbers. That X is a natural number and it's less than 0. What am I going to have here? There can't be any, right? Yeah, there's nothing in there. It's saying I want numbers that are negative. When it says X is less than 0, it's saying I want negative numbers. But I want them from the natural number system, which is all positive numbers. So you can't find a number that's negative and positive at the same time. So this is the empty set. The way to write the empty set, there's 2 ways to write the empty set. You could write the empty set with these braces with nothing in it, which is, I prefer that. I like that. It shows exactly what's going on. There's nothing in there, right? They'll write it like that, and they'll also write it like this, the 0 with the line through it. So if you write zeros, don't write them like that because that represents something. That represents the empty set. When you see this, you have to think of this also. They mean the same thing. Now, in Course Compass, it's going to say, tell me if the set's empty. They'll give you some words, and they'll say, tell me if the set's empty. One of the ones they give you, it says, the women U.S. presidents before the year 2000. Is that empty set? Yeah, that's an empty set. Yeah, can you think of a woman U.S. president? No. The next one says the number of U.S. women presidents before the year 2000. Is the set empty? Yes, it's not empty because you could answer the question. When I say the number of U.S. presidents that are women before the year 2000 or something like that, you answer the question. You answer the question with a 0. This is not empty. When I could put something in there, there's something in there. It's not empty, right? I mean, I could put any kind of symbol in there. I could put anything in there. If there's something in there, it's not empty. And since you were able to answer the question with something, it's not empty. Let's talk about the cardinality of set. The cardinal number of a set, or the cardinality of a set, all they're asked how many elements are in that set. Say I have the set A is equal to A, B, C. Then I'm going to say dot, 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 and I'm going to end it with a Z. There's my set. So that's the set of the alphabet, right? I put a dot, 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 but I ended it with Z, so you know it ends at Z. So when I look at this and I say, what's the cardinality, or what's the number of elements in the set? The cardinal number of A is how they'll say it, but I always say the number of elements in A. Notice when we use set notation, we have braces. When I'm asking a question, the number of elements in A, I'm going to answer with a number. There's no braces around it. Notation is very, very important in this section. So how many elements are in set A? 26, because there's 26 letters in the alphabet. What if I say set B is equal to 5, 6, 7, dot, 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 32. And I say, how many elements, the number of elements in B? So I hear 27, I hear 28. What do you think? So what are you doing? You're subtracting what? So you're saying 32 minus 5, and you get what? Okay, so you get 27. So I hear one answer that says 28 and one answer that says 27. So we have to decide which one it is. So I have 27 as one answer, and then the other, somebody else says 28. So which one is it? To establish a rule, or you're trying to figure out something, go back to something easy. Say if I have 1, 2, 3, you can clearly see how many elements are in there. There's 3. If I subtract 3 minus 1, what do I get? 3 minus 1 is 2. Well, that doesn't work. I can't just subtract them because I know I have 3 elements. So what did I miss? I missed, like you said, I missed adding the endpoint. When I subtract it, I still need to add a point at the end. What's the correct answer? 28. Because I subtracted them. Subtracting them, you miss one of these elements. So you have to add it back in. So you add 1. Let's just start with something like this. Let's say I have 2, 4, 6. The rule for this one. If I subtract 6 minus 2 is 4. I know I have 3 elements. It's not working. Divide by 2? Why would you divide by 2? Okay. So you're saying, let's say 6 minus 2 divided by 2. So, yeah. So 4 divided by 2 is 2. What do I do now? I mean, we know it's not 2. It's increments of 2. That's why we divided by 2. I agree. So the suggestion is to add the endpoint. That's a good idea. We're just going to see if this works. So I'm going to go up to 8 now. And I'm going to use the same thing I just did there and see if it works. So I say 8 minus 2 is 6. Divided by 2 is 3. Then what? Plus 1. That seems to work. Right? 12 minus 3 is 9. Why did I divide this one by 2? Because they go up by 2. What does this go up by? Which should I divide it by? Okay. Okay, and that equals 3. But I have 4. So what do? Add 1. So the cardinal number leads to equal sets. Are 2 sets equal? Say I have A, B, C, and set B, I'm going to say is 1, 2, 3. And set C, I'm going to say is A, B, C. So the cardinal number of each of these, the number of elements in the set. So when I say the cardinal number, I say the number of elements in A. How many elements are in A? 3. The number of elements in B. How many elements in B? The number of elements in C. Yeah, I have 3 and 4. What I didn't talk about is these need to be distinct elements. When we talk about sets, we have to only write down the distinct elements. We don't write down any repeats. So really, set C is A, B, C. And that's how we treat it. Because if there's duplicates, we don't write them. You have to treat everything as a distinct element. So these are the same. So the number of elements in C is 3. Now I want to talk about equal and equivalent. When you came into this class, you knew what equal was. Equal means exactly the same thing. It still means things are exactly the same. So don't confuse yourself about what equal is. It's exactly the same. So if I look at these and I say what sets are equal, I'm going to say set A and set C are equal because, again, I only looked at distinct elements. So you knew that coming in, so don't let that confuse you. You know what equal means. Equivalent. Sets that are equivalent mean that they have the same cardinal number. So I can say set B is equivalent to both A and C. They have the same cardinal number. All three of those sets are equivalent to each other because the numbers are the same. The elements don't have to be the same. I could say in my class, you guys are a class of 30, which is equivalent to my class of 30 in another class. You know, they're equivalent because they have the same number of people in them. But they're not equal. They're not the same people. They're equivalent because there's the same number. All my classes have 36. They're all equivalent. Okay? But to be equal, it's exactly the same thing. They have to be exactly the same, and these are. Here's what gets confusing in Course Compass. And this is what I don't like, because I think that the way they ask you the questions sometimes in this Blitzer book could be a little misleading. X such that X is greater than or equal to 2, and X is less than 5. And then, so I'm going to say this is my new set A, and I'm going to say set B is equal to 4, 3, 2. I put it in a descending order on purpose because it doesn't matter. You guys are the same whether or not you sit in the same seats every time, right? You can order them any way you want. They're still, it represents the same set of people. Okay. So what they'll ask you, here's what they'll say. The directions will say, are the sets equal, equivalent, or both? Okay, well, first of all, you want to make this into roster notation. That's the first thing you're going to do. So roster notation is going to be 2, then I go to 3, right? I go 4, and I don't include 5. Everybody agree? So we see that these are the same, right? If I look at the number of elements in A, I see that it's 3. The number of elements in B, I see that it's 3. The cardinal number is the same, so yes, they're equivalent. But I look further and I see, well, they're exactly the same. So they're equal. How can you be equal without being equivalent? You can't. You can't be equal without being equivalent, right? Because to be equal, they're exactly the same. So if they ask you, is it equal, equivalent, or both? Really, they should ask you, is it equivalent or both? So you're never going to answer the thing equal, because if they're equal, they're also equivalent.